Welcome students once again to another lecture of engineering physics. And in the engineering physics, we are once again going to discuss about as you can see, the first unit. For the first unit, we are having the quantum mechanics. This is the name of the first unit, and we will be discussing one of the topic of the quantum mechanics. So quickly, I will share with you all the topics which are in the first unit. So you can see in the slide, we are having these topics like inadequacy of classical mechanics, Planck's law, qualitative discussion, the quantum effect, and the wave-particle duality, the de Broglie concept of matter waves, and Davison-Germer experiment, phase velocity, group velocity, physical interpretation of wave function, the time dependent and the time independent Schrodinger wave equation. And lastly, we are having the particle in one-dimensional rigid box. So in today's lecture, I will be giving you a brief idea about this topic, particle in one-dimensional rigid box. And we will see that what is the condition of this topic and then how it is studied. So basically the topic, the particle in one-dimensional box, it is studied with the help of a time-independent Schrodinger wave equation. So as you can see that the time-independent Schrodinger wave equation is having this is derived from this general wave equation. So this is the general wave equation. It is having all the derivatives with respect to the x, y, and z coordinates. And on the right hand side, it is having the derivative with respect to the time coordinate. C is the velocity of light, and phi happens to the wave function, which is representing any type of wave. It is a general wave function, which is going to represent any type of wave. So this we use to obtain the time-independent Schrodinger equation. So since the discussion of the derivation is not included in the lecture, it will be discussed, it can be discussed in another lecture. So we will write down the direct expression for the time-independent Schrodinger equation. So when we use the wave function, the general equation of the wave function, so we are able to derive this expression, and this is del square psi plus 2m by h dash square, and E minus V psi is equals to 0. So this is the time independent Schrodinger equation. Here m has to be the mass of any moving particle to which the matter wave is attached, and psi has to represent that moving particle. And similarly, E is the energy of the same particle, which we will study. And V is the potential energy which the particle is experiencing due to various type of interactions. Those interactions we can discuss. The interactions are specific to the problem. So we can discuss the form of the interaction. V changes. Again, if we consider that the interaction V is 0, that means the particle is a free particle. It is not feeling any type of or experiencing any type of interaction. So then the V becomes 0, and the Schrodinger equation, this time independent Schrodinger equation, it reduces only to this part. So this much discussion, this much idea will be helpful for our further study of the topic, which is particle in the one-dimensional rigid box. So now we move on to the problem. So this is the problem, particle in one-dimensional box. So we have to study the movement, the motion, and the properties of the particle which is present in this one-dimensional box. You can see this box, it is a one-dimensional box. And you can see that this point M is representing the position of the particle which is present inside the box. And this problem is selected so that the application of the Schrodinger's equation can be studied. The students are familiar to apply the Schrodinger equation to different problems. So to make it simple, the one-dimensional part has been discussed. That means only the x dimension here is used. So we will first study about the box. So you can see this is the only dimension of the box, this x. And the boundaries are showing that one of the boundaries x is equals to 0 and the other boundary is x is equals to L. So the box is having the width only L. So this much is the dimension of the box. Since it is one dimension only, it doesn't have any representation of the height or the width. It is only having this dimension, and therefore the particle which is present in the box, it is moving in this dimension only. All right, so this is about this x dimension. Now we talk about these levels where infinity is written. So these are the walls of this one-dimensional box, and this infinity is showing that the walls are very high. So they are tending to infinite. So it is a box which is having the walls which are very high. So in this box, the particle is contained. So the particle, we can say, it is deeply inside the box. So now this is how the problem has to be defined, and this is how you have to understand the problem. Now what happens? Now this problem we have to study. So what do we do? Since no discussion of time is given in this entire problem, we don't know, we are not given that at t equal to 0 the particle is here, t equal to 5 seconds or minutes the particle is here. So no discussion of time is done. So now it is easy for us to select that which type of Schrodinger equation we will use to solve this problem. So we will use the time independent Schrodinger equation because of the fact which I just discussed, that no discussion of time has been done. So we cannot use the time dependent part. We have to use the time independent part. So we will use the time independent part. But before that, what we have to do, we have to find out that how is the behavior of the particle inside this box. What are the interactions the particle is experiencing when the particle is inside the box? So for that, we define the potential function V. This is the potential energy also we can say. So as per the discussion of the box, we can define it like this. So we can say that Vx is equals to infinite. So V is depending on x because x is the only dimension which is present. It is a one-dimensional box, we must remember. So this is infinite, and when it is infinite, when the particle is at these boundaries, so the boundaries are x is equals to 0 and L. So x smaller than 0 is actually not possible, but it is written just for the sake of the condition. So when it means that when the particle is here only. And similarly, x greater than L is not possible, but it is written just for the sake of condition that x may be equal to 0 also, may be equal to L also. So this condition is x is equals to L, and again here we can see by the diagram that these walls are tending to infinite. So by the relation of that height, we can consider that the potential energy at these ends, it is infinite. That means the particle is when the particle comes to these boundaries, then the particle experience a very large potential energy. So the particle cannot cross that potential energy. Now we have another definition also. So this was the discussion. The first line of the potential energy gives the discussion that what are the values at the boundaries, at the end points. Now when the particle is very well placed inside the box, so then what are the values? So when it is placed inside the walls, so then the potential energy is 0, because you can see, we cannot see any height component here, which can represent the potential energy. So inside the boundary, it is not experiencing any interaction. All right. So therefore, interaction has to be 0. And we will consider that when the interaction is 0, so x is between 0 and L, so that it is telling that the particle is very well placed inside the box. All right, now the discussion of the potential energy is done. Now we will move to the Schrodinger's time independent equation. So now this is our Schrodinger's time independent wave equation. So this is del squared phi by d squared phi by dx square plus 8 pi square m by h square. So this phi is here representing the wave function of the moving particle. And m, which is shown, it will be representing the mass of the particle. Similarly, capital E is the energy of the particle, and V, we have just defined the potential energy of the particle. So now we will start applying the conditions of V. So what happens? So we have to consider the behavior of the particle when the particle is inside the box. So inside the box, we will have the condition V equal to 0, because it is when it is inside the box, so the V has to be 0, this one. So we put V equal to 0 and we put this value in this equation. So when we put the value V equal to 0, so we are having this equation. And now we will solve this differential equation, the Schrodinger equation. So what do we do? To make it simple, we just substitute this entire big part of energy, 8 pi square me by h square, as some other variable, and that variable we give the name as k square, so that it becomes easy to solve. And when we solve the value of k or we solve the value of wave function, then we will substitute this and find out. So let us begin. So this is the Schrodinger wave equation, and the other part of this is, it is the second order mathematical differential equation. So we will find out the general solution for this equation. And when we work for the general solution, so we select the most general solution, which is phi x is equals to a sine kx plus b cos kx. So this is the most general and suitable solution for this differential equation. Here A and B are treated as constant, and K we already know that we have defined here, and X is the position of the particle which it is moving. So now this is the general solution, and once we know A and B, so we will be able to fully determine the wave function. So we must understand that when we are applying the Schrodinger equation to any problem, so what do? We find out the wave function, and hence we find out the energy in that problem. So that is how the solution and the application of the Schrodinger equation is done. So to find out the values of the constants A and B, you can see that we have applied the boundary conditions. So when we were discussing the box, so we have discussed that the box is one-dimensional and it is having the two boundaries. So x is equals to 0 is one boundary and x is equals to L is the other boundary. So these boundary conditions will help us in calculating the values of the constants A and B. So let us begin. So we begin with the first boundary condition, and it is x is equals to 0. So this is the first boundary. So at x is equals to 0, we understand that the phi has to be 0. The phi has to be 0 because we have understood that V is infinite. We have defined here, we have defined in this that V is infinite, right? So the potential energy which the particle is experiencing is infinite. So it will not be able to cross over the walls. It will not be able to go out of the box. So that part we have to use here. So when it will not be able to go out of the box, so we must consider that it will not stay at the boundary. So the particle will not be defined. Therefore, the wave function has to be having the value 0. So 0 is the value at x is equals to 0, and we put these conditions in the wave function, and we find that this a sine 0 and plus b cos 0 and phi of course is 0. So sine 0 is 0, we already know. So this term vanishes, and this is b cos 0. So this is giving us cos 0 is 1. So b gives us the value 0. So hence the constant b equals to 0 has been evaluated. Now we put this value of the B in the equation of the wave function, and then we obtain that the wave function phi is A sine kx. So now our wave function is this. Now once we determine the constant A, we will be able to fully determine the wave function phi x. So now we move on and take the help of the other boundary condition, that x is equals to L. This is our next boundary condition. At x is equals to L, phi has to be 0 again, because the same reason, at the boundary the potential energy is infinite, so the particle cannot cross. So, and therefore the existence of the particle at this boundary is also minimum. So we have to keep phi equals to 0 here. So again at x is equals to L, phi has to be 0. Now again we put this value of the boundary condition here. So x is equals to L this time, we have substituted L, and phi is equals to 0, we have substituted 0. And now we have obtained the relation A sine KL is equals to 0. Now we must understand that either A has to be 0 or sine KL has to be 0. Now let us see what is going to happen. So A cannot be 0. Why cannot A be 0? Because once A becomes 0, look at here that when A becomes 0, so what happens to the wave function? So it vanishes. So therefore A cannot be 0. So one part we have obtained. A cannot be 0. So definitely the other part sine KL has to be 0. Now again sine KL has to be 0, but KL cannot be 0. Why? Because L is what? L is the dimension of the box. So that cannot be 0. Otherwise the box will collapse. Alright, so the box will not be defined. So L cannot be 0. So therefore KL cannot be 0. Alright, so now if KL is not 0, so what other value can KL have? So sine KL is equals to 0. So definitely KL can have values like n pi, where n has to be some integer. So therefore KL is given the value n pi. And now the value of K is also calculated from this expression n pi L. So from the second boundary condition, what do we get? We do not get A, for which we have applied the condition. So A is still unknown. Instead, we are getting K. K is the part which we have defined, which is a variable which we have used as a definition. So we are getting another value for K. So now what do? We first understand that now what happens to the wave function. So when we understand, so we find that now the wave function phi is written as A and sine, and in place of K, we are having the value of K now, n pi by L, and we substitute here. So our wave function again becomes somewhat defined properly. So it is A sine n pi L x. All right. Now we take the help of this K again, and we have this value, we square the value which we have obtained. So we have obtained K is equals to n pi by L. So now we square. So it becomes K square is equals to n square pi square by L square. Now when we square this, so it is easy for us to compare this value of K square with the value which we have already defined. So we have already defined that K square is 8 pi square m E by h square. So now this is one value of K square which we have defined. This is another value of K square which has obtained by our calculation. So now the values will be equated. So now this is how the values are equated. And what do we find? So now we find some expression for the energy. E is the energy of the particle, which the particle is going to obtain when it is present inside this one-dimensional box. So in this way, we have the energy value. So En is equals to n square h square upon 8 ml square. So n is the integer, so it can have the value 1, 2, 3 and so on. So when we put n equal to 1, we are having the first level of the energy which the particle is going to obtain. When we put n equal to 2, we are going to have the second energy level, and so on. So in this part, we have now obtained the energy values for the particle. So this is one study which we have obtained by using the Schrodinger equation for this particle. And now let us see. Now we will again work further. Our work is not complete because why? Because the wave function phi, we can also have the wave function phi cannot still be fully determined. Because why? Because a is still left. The constant a is left. It is unknown. So now we work for the evaluation of constant a. So what do? We take the help of this normalization condition. So what happens whenever we are defining a wave function and it is used in the Schrodinger equation, it is defining a particle which is showing the dual nature. So the wave function has to satisfy certain conditions. So one of the very important conditions that the wave function must satisfy is that it must be normalized. So now we apply that normalization condition to our wave function phi. All right, and we see that whether the phi can satisfy this normalization condition, or if it satisfies, so then what must be the value of a? For what value of a, phi becomes a wave function which will be satisfying this normalization condition. So condition is like this. Condition says that suppose we are having the wave function and it is represented by suppose psi. We can consider this psi just for the sake of the condition. And then we take the mod of that psi. This is psi mod square. So this psi mod square is called the probability density. All right. And this is when multiplied by dx. So it becomes the total probability. So probability density is psi mod square and multiplied by dx. So it becomes total probability. And now this is the range 0 to L because the box is having the boundaries 0 and L. So the range of the particle, the range of the wave function has to be from 0 to L. So now this whole expression is telling that the total probability for the particle to exist inside this interval 0 to L has to be just 1. So this is what the normalization condition says. It says that the total probability that the particle is present in a region is 1. So this is and the condition becomes like this. So what do we do now? We have to just find out that for what value of a this condition is satisfied. So we just substitute our wave function which we have determined. We have determined, if you remember, we have determined the wave function phi like this. So we will substitute this entire wave function here. And you can see that after substitution, we are having a square and we are having sine square n pi x by n. And we are having dx also and is equals to 1. So now it will be solved. All right. So now when it will be solved, simplified, and you can see these steps how this is the simplest form. Now it has been converted into cos and then now it has been integrated and the limits are substituted 0 and L and the value of the a is determined. So now the value of the constant a is 2 by L. L has to be the dimension of the box and the square root also. All right. Now we will substitute this value of a in our wave function and we will find out that the wave function phi becomes 2 by L square root sine n pi and x upon n. So now this is our wave function which is giving us the information about the particle which is moving in this one-dimensional box of dimension L. All right. So this is how when we use the Schrodinger equation for any problem, So we are evaluating the wave function and we are evaluating the energy values. So these are the main results which we are obtaining when we apply the Schrodinger equation to any problem. All right. Further, we can plot a graph of our wave function with respect to the distance, and we can have more information about the behavior of the particle. Like in this graph, we have the graph of the wave function and the position of the particle in terms of x. So these are the boundaries. X is equals to 0, x is equals to L. And we can see that if the particle is in n equals to 1 energy level, so its wave function is determined by psi 1. All right, n is equals to 1. So, and we will substitute n equals to 1 and we will be having this type of wave function. Now, when we move about the n equal to 2 state, the particle is n equals to 2 energy level. So the behavior of the wave function is like this, and similarly for n equals to 3. More study we can do in terms of probability density. We can plot the probability density also for the different states of the particle. Like for here we can have n equal to 1 state, this is psi 1 mod square. N equal to 2 state we can have, this is psi 2 mod square. And n equal to 3 state we can have psi 3 mod square. So in this way, the complete study of the particle in a box using the time independent Schrodinger equation can be done. All right, and now we can discuss some of the numericals which are asked in the examination about this problem. So in the first numerical, we can see that what the numerical is asking, the question is saying that find the energy of an electron moving in one dimension in an infinitely high potential box of with 1 angstrom, and mass of electron is given already, and the Planck's constant h is also given. So what do? We write down the expression of the energy directly, and we have just obtained. So we already know what is the expression. So the expression is E is equals to n square h square upon 8 ml square. And they are asking that we have to find the energy of an electron. So moving in one dimensional. So we can just find for n equals to 1 because they have not mentioned any energy level. So we can just find out one level, minimum energy level. So for that, we will substitute n equals to 1 in this expression. And the remaining values are given, like h is given. So we will substitute the Planck's constant from here. And value of the mass of the electron is given. So we will substitute the mass of the electron. And what else? And L is given 1 angstrom. So we will substitute this in terms of meter. And we will solve these values and we will be obtaining the values in the joules like this. And further, it has been converted into electron volts because mostly in the electron volts, the energies are mentioned. So therefore, it has been converted. So for you also, it is convenient to see how the joules part is done and how it is converted to here. The units have to be properly substituted in the numericals. Then another numerical we can have. In this numerical, it is saying? It is saying that a particle is confined to move along x-axis and it has the wave function psi x, and the expression of the psi is ax, and it is moving between x is equals to 0 and x is equals to 1. That may appear x is equals to 10, but actually it is 1.0. So x is equals to 1. And for these regions, psi is defined as x is equals to ax, and elsewhere psi equals to 0. For other regions, the psi is equals to 0. This is how the wave function is defined. Now we have to find the probability that the particle can be found in x is equals to 0.35 and x is equals to 0.45 region. Within this region, what is the probability that the particle can be found? And also we have to find out the expectation value, which is of x of the particle's position. So we will begin now. So we have already discussed in the problem that this x mod square multiplied by dx. It is defining the total probability. So the same part is shown here, that the probability is x1 to x2. These x1 and x2 are the limits, are the range of the region, and this xn mod square and then dx. So now we substitute xn equals to ax, because in the region x is equals to 0 and x is equals to 1, it is defined as ax, and in the other regions it is 0. So we will substitute ax here. Now limits, we will substitute what is asked in the question. Like they are asking x is equals to 0.35 to x is equals to 0.45. In this region, they want to find out the probability. So we will substitute the limits like this. All right. And then we will simply integrate. All of us know how to integrate these simple values. So when we integrate, so this is the result of the integration. Now it's time to substitute the limits. So the limits are substituted and hence the evaluation is done. And since a is given as it is and no other value of small a is given, so the answer has to be calculated in terms of this small a. And if we calculate, so we are having 0.0161 a square. So the calculations have to be done very carefully. So here the one part of the question is solved. That means the probability of the particle has been calculated in the given region. All right, now the next part, the expectation value we have to evaluate. All right, so expectation value we have to find out, and this is the expression of the expectation value. And we will substitute this expression. You can see psi x is substituted. And we will solve, and it becomes x cube dx. And now we integrate and we substitute these values, the limit 0 to 1, because no limits is given here. So we will take the whole limit 0 and 1 between which the particle is defined. So the expectation value comes out to be this. So this much discussion of the numerical along with the discussion of the problem, I think it will be helping you a lot to understand this problem, particle in one-dimensional box, and you can try more problems related to this topic. All right, and I will be quickly sharing these references which I have used, and you can also use these references and for the detailed discussion of this topic. All right, and these are the internet site also, you can visit them also. Thank you all of you for watching this particular topic and showing interest in this. We will return with a new topic soon. Thank you.